Hi there, welcome to Explain This, a podcast where we try to explain complex things in simpler ways for people of all ages. I'm your host Jen Kim, and today we'll talk about mirrors. Let's get started. Mirror, mirror on the wall, who's the fairest of them all? And who said that quote? You might say the evil queen from Snow White, but actually, turns out she never said mirror, mirror. She says magic mirror on the wall, who's the fairest one of all. Yet another tragic collective false memory quote, much like the infamous elementary my dear Watson. Anyway, mirrors have been an integral invention/discovery in human history. We use mirrors all the time in daily life, from checking out how fabulous our butts look, to seeing if it's safe to back the car out, or applying makeup, etc. We also know that we can use mirrors for fun stuff, like a mirror maze, secretly annoying a classmate by shining light in their eyes, or summoning ghosts by saying their name over and over. But as common as they are and how often we use them, there's probably a lot you don't know about mirrors as well. For example, do you know what the color of a mirror is? Did you know that mirrors can be used to make a death ray, or see the stars in detail? And probably the most perplexing question, what's the mirror flip left and right, but not top and bottom? All this and more in today's episode, so without further ado, let's explain what a mirror is and how they work to you as if you were a child. When you look into a mirror, what do you see? That's right, a super handsome and pretty and amazing person who can do whatever you set your mind to. You probably already know that a mirror lets you see not only yourself, but what's behind you as well. It's almost like a mirror is a portal to another world. If a mirror is clear enough, it looks like you can reach in and touch your own face. This is because of how mirrors, and more importantly, light works. You can think of light super simply by imagining it as an energy beam. If you don't get in its way, light travels in a perfectly straight line forever and ever. It's also not just one beam, but a bundle of different colored beams. There's red energy beams, blue beams, green beams. There's even colors you can't see, like ultraviolet or X-rays. When all of these beams are sitting next to each other, they combine to form white light. When this light beam hits something, say an apple, the apple scatters the light beam. Kind of like if you turn a hose on and spray a rock, the water bounces off the rocks and scatters everywhere. Likewise, some of the light beam is sucked up by the apple or absorbed, like a rock soaking up water. But because every color beam is a little different, they play differently with each surface. A red apple, for example, will bounce off red beams, but suck up blue beams. Because mostly red beams are bounced off, these can carry on traveling straight until they enter your eyes and be seen by you. Since the apple is bouncing off or reflecting mostly red beams, it looks red. That's how colors work. Now, mirrors are special. They're so perfectly flat that it reflects all the light beams. Even better, it doesn't even scatter the beams. The beams hit the mirror, then get bounced off at exactly the same angle, like a pinball hitting a wall. Ping, ping, ping. Okay, so for this bit, you have to use your imagination. Imagine that you're sitting in front of the mirror, head on. The sunlight from the window hits your face and scatters, reflecting back the light beams that make up the color of your skin. This reflected light then travels forwards from your face, hits the mirror, and then here is perfectly reflected back at you at the same angle. So if the light from your left cheek is hitting the mirror at a diagonal, that light will get bounced back to the right side of your face at the same diagonal angle. Which means, when that light finally hits your right eye, your eye will think that the light came from behind the mirror, because light always travels in a straight line. Even better, it will think it came from the left half of the mirror, because of the angle. This is why the left half of your face appears on the left half of the mirror, and why mirror images look flipped. But then, why doesn't it get flipped in a way so your head appears where your feet are, and vice versa? Well, for that, you'll need to grow up and listen to the rest of the podcast as an adult. Alright, so mirrors seem super simple until you get down to the nitty-gritty of it. The essence of it is as we've said. Light is made up of lots of beams with different wavelengths, all of which travel in a perfectly straight line. A mirror is a perfectly flat surface that is so polished and flat that light gets reflected back perfectly, exactly at the same angle. No scattering or absorbing or anything. We call this specular reflection, and it's very satisfying to see on a diagram because the angle that the light hits the mirror, the angle of incidence, is exactly the same as the angle that the light leaves the mirror, the angle of reflection. Put simply, imagine a horizontal line on a piece of paper. This is the mirror. If you draw a line from the bottom of the paper extending up, hitting the mirror line at 45 degrees, then the line will hit the mirror and bounce back towards the bottom of the paper, again at 45 degrees. If the line hits the mirror at an even steeper angle, say 60 degrees from the mirror, then it leaves the mirror at the same steep angle, 60 degrees. This means that if you shot a line towards the mirror head-on at 90 degrees, then the line will bounce back perfectly along its original path, because that's 90 degrees, or perpendicular to the mirror. It's a bit of a palaver explaining geometric diagrams over a podcast, so I'll make sure to include a diagram in the show notes so you can visualize it. Now, because the angle of incidence and the angle of reflection are identical, to your eyes, it looks like the light ray came from behind the mirror line, coming at you at the reflected angle. You can test this yourself the next time you're standing in front of a mirror. If you put something in between you and the mirror, say a banana, the distance between the banana and the mirror will be equal to the distance between the mirror and the reflected image of the banana. Then, if you move the banana 10 centimeters to the right, the reflection will also move 10 centimeters to the right. Now, the reflected banana is at an angle with you, and that angle will be exactly the same as the angle the original banana is to the mirror. If you move the banana backwards towards you, it looks like the reflected banana is moving further from you, deep into the mirror world. Essentially, the reflected banana behaves as if it's moving around behind the mirror. Okay, I know it's a hard concept to imagine without looking at a diagram or testing it yourself, so have a play around with it when you're able. And if you've grasped this concept so far, then good, you're doing super well. So to quickly summarize how mirrors work, it reflects all light back at the same angle that the light hit the mirror at. Because of the two angles being the same, it looks like the object is exactly that angle and distance, but deep in the mirror. Now, we can talk about mirror images. You'll no doubt have noticed that in a mirror image, it looks like everything is flipped horizontally. When you wave your left hand, it looks like your reflection is waving their right hand. If you write something on a piece of paper and show it to the mirror, the reflected text is really hard to read because it's been inverted. This is why Da Vinci wrote all of his notes in mirror writing, so people couldn't copy his cool ideas. The cool thing is, you can cancel out a mirror image by using another mirror. This is called a non-reflecting mirror. Basically, if you put two mirrors side by side, then angle them so that they're 90 degrees from each other, then light hits the first mirror, reflects and hits the second mirror, then reflects and hits you. Because the light has been reflected twice, the image no longer looks flipped. When you wave your left hand, the reflection waves its left hand back to you, and you can see everything on their t-shirt as if they're a real person in the real world. But back to normal mirrors, because we have lots to talk about. A mirror image is interesting because it's almost exactly like the original, but there's some key differences. For one thing, it's flipped, so if you care about the orientation of things, such as how letters look in text, then it might look completely different as a mirror image. If you're a shape such as a square or a starfish, then it doesn't matter if you're flipped and reflected, because the reflection will look the same. But many letters and numbers, such as F and 5, aren't symmetrical that way. Their mirror image looks completely different. If you took an F and a mirror F and overlaid them, they wouldn't overlap. Bits will stick out. This is called an axis of symmetry. If you drew a line down the middle of the shape and folded it along that line, will it perfectly overlap or not? If it does, it's symmetrical along that axis. Some things are symmetrical horizontally but not vertically, like a capital M. Some things are symmetrical only when you rotate them, like the letter Z. You can rotate it 180 degrees and it will still be a Z. Then there's the circle, which is symmetrical in every way. Now, when you take something that isn't symmetrical, such as your foot, then reflect it in the mirror, the reflected foot will not overlap with your hand. Essentially, your left foot will turn into a right foot in the mirror. This means that your left shoe wouldn't fit your reflected foot. You might be wondering at this point, Jen, why are you going on and on about mirror images when it's just a reflection? I'm obviously not going to try and put my shoe on my reflection. But you see, this concept is very important in another field, chemistry. And as you'll know by now, if you've been listening to the show, your body is made up of chemistry. All matter is made up of atoms, which can link up with each other to form molecules. Many molecules have exactly one shape because the way atoms can be arranged follow very strict physics laws. For example, water molecules always look exactly the same. one oxygen in the middle, with two hydrogen atoms sitting slightly diagonal to it, like Mickey Mouse ears. But some molecules can be arranged in various ways. Imagine a molecule that is made up of 5 different colored atoms: black, white, red, blue, and green. The black atom can have 4 friends, or bonds, while all the other atoms can only have 1 friend. So if you have a molecule made up of exactly 1 each of these atoms, then there must be a black atom in the middle, and then all the other colored balls hanging off it like limbs. So to make it easy, let's put the white atom above the black atom, like a head. Now all we have to do is arrange the red, blue, and green atoms beneath the black atom. Easy. But turns out there are 2 ways you can do this. Firstly, you could have red, then blue, then green atoms in clockwise order. But what if you switch the blue and the green atoms around? Now the arrangement is just different enough that you can't overlap the 2 variations of the molecule over each other. The green and blue atoms would be flipped from each other. Essentially, one version looks like a left foot, while the other looks like a right foot. They can't share shoes because they're different shapes. Even though the molecular formula would be exactly the same, the layout and handedness make the molecules different. This is called chirality and has surprisingly dangerous consequences. Turns out, molecules can behave completely differently depending on what orientation their atoms are. We call these different versions of a molecule enantiomers. And funnily, chemists use left-handed and right-handed to distinguish different enantiomers. Except they're serious scientists, so they use Latin. Dextro for right-handed, levo for left-handed molecules. Side note, the other Latin word for left-handedness is sinister. This is where the word comes from. They used to think left-handed people are evil because humans are inherently prejudiced. Anyway, back to enantiomers. All kinds of chemicals can have enantiomers, including those that make up us and food. Amino acids, the building blocks of proteins. An amino acid called carvone has 2 enantiomers. The left-handed L-carvone that tastes like spearmint, and a right-handed D-carvone that is tasteless. Cool, so enantiomers can taste different. Big whoop, right? But medications can also have enantiomers. The most well-known example of this is the infamous thalidomide. This drug was invented to help with morning sickness and provide a sedating effect for pregnant women. But what the pharmaceutical company didn't realize was that only one enantiomer of thalidomide had this desirable effect. Turned out, the other enantiomer was a powerful teratogen, a chemical that can disrupt the way an unborn fetus can develop in the womb. In the case of thalidomide, it led to over 10,000 babies being born with birth defects such as missing or shrunken limbs, causing lifelong disabilities, because they didn't respect the scary power of mirror images. Fun fact before we move on from mirror images. It's very likely that Lewis Carroll, the author of Alice in Wonderland, knew all about enantiomers and how mirror images can have dangerous consequences. The sequel to Alice in Wonderland, Through the Looking Glass and What Alice Found There, is all about a mirror world, where things are almost the same but quite different and quirky. Alice literally steps through a mirror to enter this world. She finds characters such as Hatter and Hagar, who are the mirror images of their first book counterparts, the Mad Hatter and the March Hare. They seem familiar, but don't recognize Alice at all. The 2 books have a lot of similarities as well, but with mirrored differences. The first book is set outdoors in summer, changing size as a plot device, and trump cards are the main theme. The second book is set indoors in winter, changing directions as a plot device, and chess is the main theme. Even more interestingly, there's a scene where Alice picks up a bottle of milk and decides not to drink it because, to quote, perhaps looking glass milk isn't good to drink. Now, Carroll was a mathematician and had many friends in the sciences, so he probably was familiar with the concept of chirality, which was discovered around his lifetime. So it sounds like an innocent fairy tale line, but it carries a lot more scientific significance. It's fun to think that mirrors have always been associated with some amount of mystery and horror in folklore and literature. Think of how many horror stories include mirrors. Bloody Mary, Candyman, Us, Black Swan, the whole 7 years of bad luck when you break a mirror. People have probably always been fascinated with how mirrors look like a portal to another world that seems like ours, but subtly different. Alright, so now you know that mirror images aren't the same as reality, and might even be dangerous. Let's talk about the real question. What's up with the whole flipping thing? Why does a mirror flip horizontally but not vertically? We'll answer that after this break. Welcome back. So one of the big reasons I wanted to do this episode was to explain to you why mirrors seemingly only flip in one direction, horizontal. That is, your left side becomes the right side of the reflected image, and texts look like they're written backwards. This seems to also apply to movement. If you move a banana to your left side, it moves to the reflected image's right side. But the same doesn't seem to apply for top and bottom. The reflected image's head is still on top of its body, and words don't seem to flip upside down in the mirror. How does the mirror know how to selectively flip only horizontally? Maybe mirrors are magic. Of course not. It's not magic. It's just science. Oh, and before you say, Jin, it's obviously because our eyes lie side by side, so the reflection's horizontal. Duh. But you'd be wrong, because you see the same kind of mirror image with one eye closed. Let's start with the basics. Words. We think words look backwards in a mirror because we present it to the mirror backwards. Boom. Think about it. To read something in the mirror, you face the words away from you. The words on your t-shirt are facing away from you. And since you're showing the mirror words that are flipped to you, it's reflecting back flipped words. Put it this way, if you write your name on a piece of paper, then showed it to another person in front of you, they'd be able to read it fine. But if you try to read the words as you stand, say if the paper happened to be transparent, then the words would be flipped back to front. You can visualize this by writing something on a transparent piece of plastic or glass, then holding it up to the mirror. You'll notice that what you see in the mirror is exactly what you see through whatever you wrote on. And that's right, the mirror was honest all along. It's also flipped horizontally because you flipped it horizontally. Because that's how we show other people writing. We'll turn the page sideways, not flip it top to bottom. If you did that to the mirror, then it would be flipped vertically as well. So, now that we have words out of the way, let's go deeper in understanding why a mirror image looks the way it does. Even though you think the horizontal directions have flipped, it kind of hasn't. Think about it. If you hold a banana up to a mirror and move it left, it's also moving left in the mirror. Same with up, down, and right. The banana in the mirror copies the exact motion. The issue is that we're personifying our reflected image, assuming that the banana is moving in relation to our reflection. So even though the banana is moving to our left, because we see a person in the mirror, we automatically define the banana as moving to their right. This is because human beings happen to be pretty symmetrical horizontally. Our axis of symmetry runs from the top of our head to between our feet, right down the middle. So even when we're flipped in the mirror, we look pretty normal. This creates a bit of a psychological trick, where your brain thinks that the reflected image exists as if a person that looks like you has gone around the mirror and facing you. But that's not what happened, right? We notice from the left hand, right hand in that shimmer example. Plus, human beings tend to turn around horizontally to look behind us, rather than flipping ourselves vertically to do a handstand, so that also fits into this. So, here's the big bombshell revelation. You ready? The mirror isn't flipping you horizontally or vertically. It's actually flipping your depth. To illustrate this, think of the banana again. Although left, right, up, down are copied by the mirror, one axis of direction is actually reversed when you move the banana towards or away from the mirror. If you move the banana further from you towards the mirror, the reflected banana moves closer to you, and vice versa. That's right, the mirror is reflecting along an axis of symmetry that connects you to the mirror. In mathematics, we call the horizontal axis the x-axis, and the vertical axis the y-axis. Depth in three-dimensional space is called the z-axis, and this is exactly what's being flipped by the mirror. Another way to think of flipping the z-axis is that the mirror is showing an image that is inverted through the object. Picture a glove on your left hand, with your left hand pointing its fingers towards the mirror. If you carefully remove the glove by flipping it inside out off your hand, you'll find that the inverted glove looks like a right-handed glove. It will no longer fit your left hand, because it's an enantiomer. And this is the real secret of mirrors. And you can prove this too. We've been talking this whole time of mirrors that are on a wall, facing us directly. But what if we put a mirror above us, facing down? Now the perspective has changed. Our left shoulder and right shoulder will be reflected just the same, but because we're being inverted through ourselves from our toes to our head, the reflected image will show us upside down, as if we're standing on our heads. So there you have it. Mirrors do reflect selectively, but not on the axis you thought. It's the depth that's being flipped, not left and right. On a linguistic side note, one funny thing is that when we use the word mirror as a verb, we often use it incorrectly. As we've talked about, a mirror image should be inverted. But when we use mirroring, like screen mirroring or mirroring behavior, what we're really saying is that we're copying something. Because when you screen mirror your phone to a TV, the images aren't being flipped. Perhaps deep down inside, we know that mirrors aren't playing tricks on us. It's just honestly reflecting light back at us at exactly the same angle. It's not trying to obscure your words by making them unreadable. That's what you've shown it. Anyway, that's enough about mirror images. Let's talk instead about all the cool ways we can use mirrors, from checking ourselves out to studying stars. Mirrors are useful because they let us see things that we can't normally see. We can see what is behind us without having to turn around, and best of all, we can see what we look like. Sure, nature has some crude mirrors like a calm pool of water, but you can't peer over a pond every time you need to fix up your hair, right? This is why humans have been using polished stones and metals as mirrors since 6000 BC. The kind of glass mirrors we use now, where you have a clear piece of glass with a polished metal backing, has been around since at least the 3rd century. So it's pretty old tech, and for almost the entirety of recorded history, human beings have wanted to look at their own faces. But there's so much more you can do with a mirror than simply checking out how fabulous you're looking today and telling yourself that you can achieve anything you set your mind to, as important as that is. For instance, mirrors let us see blind spots in our vision, such as a side and back mirror in a car. There are even special curved mirrors that let us see a wider field of view, so we can look around corners and avoid getting run over. You can use mirrors to signal people by shining light in their direction. This is probably the best way to grab the attention of search parties when you're lost in the desert, because light travels faster and further than sound, as long as there are no obstacles. One-way mirrors are great for creating a room that feels isolated, while allowing observers to sneakily look inside, whether it be a simulation or an interrogation room. This is done using mirrors that have only half silver backs, meaning that only half the light is reflected. The other half just shines through like a tinted window. This means that if you keep it dark in one room and bright in one room with a one-way mirror in between, the bright room will cast a lot of light on the mirror, half of which will shine through to the dark room. Thus, the people in the dark room can see through the mirror into the bright room. But the dark room doesn't have enough light to shine through the mirror, so the people in the bright room only see their own reflections in the mirror. There's too much reflected light from the bright room, so any light from the dark room is overpowered. This is the same reason why you can see through home windows much easier at night, when it's dark outside and bright inside your house. Cool, so we can use mirrors to be creeps. What else can we do with mirrors? If you make two mirrors face each other, what do you think will happen to the light? Remember that thanks to specular reflection, light will bounce off a mirror at the same angle that it hits the mirror. So if there are two mirrors parallel to each other, light will infinitely bounce between the two. You can use this illusion to create something called an infinity room. If you were to look into one of the parallel mirrors, it will look like you created an infinitely stretching tunnel extending deep into each mirror. You can use this illusion to create something called an infinity room, where all the walls are lined with mirrors. This will result in a room that looks like it stretches infinitely out in all directions, with infinite you and whatever else is in the room. It's a dazzling experience if you ever have the chance to go in one of them. The best part about this trick is that this is how we make lasers. A laser is essentially two mirrors facing each other with something called a gain medium between them. This gain medium has a special property where, if it's powered by electricity, it can amplify light traveling through it. The physics behind it is a little complex, but essentially, light passing through the medium excites the atoms in the gain medium, triggering it to release more light, which results in even more atoms getting excited and releasing light, until you have a chain reaction. All of this light gets bounced back and forth between the two mirrors so that it keeps getting amplified. Eventually, you let out the massive amount of light through a teeny tiny opening, so it's concentrated into one powerful laser beam. This isn't the only way you can make a death ray using mirrors either. There's records from ancient Greece that the famous Archimedes of Syracuse used a massive array of bronze mirrors held by soldiers to concentrate sunlight onto invading ships, setting the wood on fire and protecting a city. Now, unfortunately, modern experiments have shown that this was probably an exaggeration, because it takes way too much time and coordination to focus all of the mirrored sunlight onto one spot, that it wouldn't have been an effective death ray. But then again, these burning mirrors might have been used to blind the naval soldiers instead. Mirrors have been indispensable in the world of art as well. Remember back in episode 31 that Brunelleschi used mirrors to help discover perspective and draw it accurately? If you don't, guess what you should listen to after this episode. We also know hundreds of artists used mirrors to draw their self-portraits, with some creative work such as MC Escher's Hand with Reflecting Sphere. Lastly, there's quite possibly the best invention involving mirrors, the reflecting telescope. Turns out that because mirrors perfectly reflect light, a curved mirror actually ends up acting like a lens. Think back to how the reflected light looks like it comes from behind a mirror. Anyway, Isaac Newton was able to invent a telescope based on mirrors instead of lenses in 1668. Which ended up being far superior to the lens-based telescope at the time. The images were clearer, and it was way easier to scale it up in size, so you could see further and further deep into space. Basically, the light that comes into the telescope is reflected by a concave mirror that concentrates all the light into another smaller mirror pointing the other way, which concentrates the light further into the eyepiece. This lets the telescope collect a massive amount of light and train it all onto your eye, so that you can see things very far away, like stars. If you've heard of the James Webb Space Telescope, or Hubble, they're all types of reflector telescopes. Pretty much all of our modern astronomy is based on what we can observe with these telescopes, so it turns out mirrors are really important. Alright, let's take one more break, and we'll move on to the last section of today's episode, where we'll talk about how mirrors can reveal a lot about our inner selves. We talked about how mirrors are quite intuitive to use, and most people will automatically know that a reflected image is not real, and that it represents themselves. But turns out, that's a pretty unique ability for human beings. If you show a cat or a dog a mirror, they can't really comprehend it, and think there is another animal on the other side of this invisible wall. Which is fair, because that's what we see in a mirror as well. It's like a portal to an alternate universe. It's just that we know what mirrors do, and we know what we look like. It turns out that most animals are not able to tell that their reflections are them. This is called the mirror test, and scientists use it to study if animals have a sense of self-awareness. So far, only a handful of animals have passed the mirror test. The great apes, such as chimpanzees, gorillas, and orangutans, certain dolphins, orcas, elephants, and the European magpie. That's not a long list. These animals are all considered pretty intelligent, and this higher order intelligence probably has something to do with the fact that they recognize that it is their own reflection that they see in the mirror. The way this shows is they'll look in the mirror, identify that it's themselves, and do things that show that they understand that it's a reflection, such as looking at their teeth or pointing to a little spot in their face. Now, the mirror test isn't a perfect test. We don't even know if it perfectly represents self-awareness, because animals who fail the mirror test may show other signs that they know that they're a living being with a sense of self. But it's a pretty interesting use of mirrors nonetheless. If you think about it, mirrors are actually quite honest. The mirror isn't trying to play tricks on you by flipping text backwards, it's just you showing it the text the wrong way round. Light reflects perfectly back at the same angle that it struck the mirror, and unless the mirror is curved or not pure, there's no distortion to the image. Now, we could apply the same principles of this honest mirror to something that isn't physical or tangible. The mirror of the mind. Humans are amazing creatures. Not only do we have the ability to recognize ourselves in physical mirrors, but we can literally reflect in our own mind. We can study how we behave and how we feel in a given situation, being mindful of our inner self. We can reflect on the past and learn from our experience to try avoid making the same mistakes, or remember useful things to try again next time. More importantly, we can reflect on who we are by looking at the reflection of our self-image in our mind mirror. Just like how we check our hair and clothes and makeup in the mirror, we can peruse our self-image. What do we enjoy doing? What drives us? What are our weaknesses or vices? Who are we? Part of the human condition is that we're constantly questioning who we are and molding ourselves to the best version of ourselves that we're content with. Through reflection, we can identify parts of ourselves that we like, parts that we want to change, and how we're progressing in that journey. Of course, many people aren't happy with what they see in the mirror. It can make us act like animals who failed the mirror test. We might try to attack it because we feel threatened, or we might become avoidant because we're disgusted and disappointed in our reflection. But we are human beings who know what mirrors do. So next time that happens, you can try to soothe and remind yourself that your inner reflection is merely an image that represents you. You don't have to like what you see, but you need to accept that it is you in the mirror, not someone that looks like you. If you don't like something about it, we have the capacity to change and grow and adapt. If you do like what you see in the mirror, then good on you. It's a great state of mind to be in, to be best buddies with your inner self. Learning how to hold the mind mirror up to your self-image and studying what you see in it is a great life skill that will help you grow and become more comfortable in your own skin. Mirrors, aren't they useful things? So what did we learn today? We learned how mirrors reflect light and make it look like we're staring through a portal into another world. We learned that mirror images might not overlap and create similar looking but very different objects called enantiomers. We also learned that enantiomers can have wildly unpredictable effects, like turning foods and medicines into poison, so don't drink things in the mirror world. We learned that mirrors look like they're flipping an image horizontally but not vertically, because in reality it's flipping the depth of an image along the z-axis. We learned how mirrors are made, and how it can be used for all sorts of things, like in telescopes, lasers, and one-way mirrors. We learned about the mirror test and how most animals can't recognize themselves in the mirror. Lastly, we learned that we are able to reflect on our inner mind mirrors, so that we can learn about who we are, and grow to be a person that we're content with. Alright, for today's 2-Minute Explain, let's talk about the color of a mirror. What? I thought we literally spent an entire episode talking about how a mirror is technically all the colors, because it reflects back all the light. But turns out the real world isn't as simple as that. We don't live in a world of spherical cows in a vacuum. So yes, an object's color is determined by what parts of the light spectrum that it reflects, as opposed to the light that it absorbs. Now, you would think a mirror doesn't absorb any light, but it does. Glass mirrors are made with a flat pane of glass over a metal backing. In the old days, this was literally a thin sheet of metal such as gold, silver, or amalgam, which is mercury combined with silver. The mercury could be evaporated, leaving only silver. This is clever because metal mirrors suffer from tarnishing and need constant polishing, whereas glass maintains its flatness quite well and will protect the metal. Nowadays, mirrors typically have a silver backing, which is applied using various fancy scientific ways such as electroplating or chemical disposition. Because glass isn't 100% transparent, some light is absorbed by the mirror. It's a teeny tiny amount, like way less than 1%, but it's some light nonetheless. If you break down and study the light that mirrors reflect, you notice that more green light is reflected compared to any other color or wavelength. You can see this in the infinity mirror example as well. If you peer into that infinite tunnel made by 2 parallel mirrors, you notice that the tunnel gets darker and darker, with a slight greenish hue. This is because with every reflection, a small portion of light is absorbed and lost, so the reflection slowly gets darker. And because green light is reflected most, the last light to remain is some green light. So it's almost an infinity room. Anyway, this means that technically speaking, mirrors are a very, very, very light tinge of green. Who knew, huh? Well, that's it for today. Thank you for listening to Explain This. I hope you've learned something interesting and maybe even useful today. We'll see you next time. Bye for now. Explain This was written and hosted by me, Jin Kim. If you'd like to suggest a topic or just send a lovely message, you can email me at explainthiscast@gmail.com or follow me on Facebook or Twitter